For 20 years, the single biggest obstacle standing between quantum computing and reality was a number so large it made the entire field sound like science fiction. To build one reliable working unit of quantum information, a so-called logical qubit, engineers believed they would need to wire together thousands, sometimes millions, of fragile physical qubits just to correct the constant stream of errors that quantum information is prone to. Millions of qubits, not thousands. Millions. That number alone pushed useful, fault-tolerant quantum computers decades into the future, past most of our lifetimes, according to some estimates. And then a team of researchers at the University of Chicago did something almost nobody expected to happen this soon. They found a shortcut. Not a workaround, not a patch, an actual structural fix to the math and the hardware underneath quantum error correction itself, one that could cut the number of qubits needed by a factor of 10 to 20. If that holds up at scale, it doesn't just make quantum computers a little more efficient, it rewrites the entire timeline for when they finally become useful. To understand why this matters so much, you need to understand exactly why quantum computers have always needed so many qubits in the first place. A quantum bit, or qubit, is not like the zeros and ones inside your laptop. A qubit can exist in a blended state of 0 and 1 simultaneously, a property called superposition. And that is exactly what gives quantum computers their power. But that same property makes qubits almost unbelievably fragile. The tiniest disturbance, a stray photon, a vibration, a fluctuation in temperature can collapse that delicate state and corrupt the information inside it, a process called decoherence. Classical computers barely have to think about this. A bit sitting in your phone's memory is essentially immune to a passing gust of electromagnetic noise. A qubit is not. It is one of the most sensitive physical systems humans have ever tried to control. Because of that fragility, quantum computers cannot just run calculations directly on raw physical qubits and trust the answer. They need error correction, a way of constantly checking whether something has gone wrong and fixing it before the mistake ruins the entire calculation. The standard approach the industry has leaned on for years is called the surface code. It works, and it has been demonstrated successfully by companies like Google, which used it to show that errors can actually decrease as you add more qubits to the system, a genuinely important milestone in its own right. But the surface code comes with a brutal cost. To protect a single logical qubit using a surface code, you often need somewhere between 100 and several thousand physical qubits, all wired together in a fixed grid, constantly checking each other for errors. Scale that up to the number of logical qubits you'd actually need to run a genuinely useful quantum algorithm, something like simulating a new drug molecule or breaking modern encryption, and you're suddenly talking about needing millions of physical qubits just to get started. That is the wall. That is the number that has haunted the entire quantum computing industry since the field began. To put that overhead problem in real terms, think about what it would take just to run one of the algorithms quantum computers are famous for being able to do in theory, like factoring extremely large numbers to break modern encryption. Estimates for how many physical qubits that kind of calculation would require under a traditional surface code have historically run into the tens of millions. Even as those estimates have come down over the past couple of years, thanks to smarter algorithms, they've mostly still landed somewhere in the hundreds of thousands to low millions. That is the scale of hardware the surface code approach demands. And it's precisely why so many experts for so long treated genuinely useful quantum computing as something that belonged 2 or 3 decades in the future rather than something worth planning around today. There's always been a theoretically better option sitting on the table, a class of error correction called quantum low-density parity check codes, or QLDPC codes for short. On paper, QLDPC codes are dramatically more efficient than surface codes. Instead of comparing each qubit only to its closest physical neighbors, the way a surface code does, a QLDPC code compares information across qubits that are far apart from each other on the chip, catching more errors with far fewer physical qubits overall. It's a bit like the difference between a small town where you can only ever check in with your next-door neighbor to see if something in the neighborhood seems off, versus a network where you can instantly compare notes with people scattered all across the city. The second approach catches inconsistencies far faster and far more efficiently, but it obviously requires a way for those distant people to actually communicate with each other in the first place. Researchers have known about the mathematical promise of QLDPC codes for years. The problem was never the math. The problem was building it. Comparing far apart qubits requires long-range wiring and connectivity that traditional fixed quantum chip architectures simply cannot provide. You can't run a wire between 2 qubits that were never physically designed to talk to each other. For years, QLDPC codes were the error correction method everyone agreed was better in theory, and nobody could actually build in a working machine. This is exactly where the University of Chicago team's breakthrough comes in, and the solution is almost elegantly simple once you hear it. Instead of trying to build fixed permanent wiring between every qubit that might eventually need to communicate, why not just move the qubits themselves? The research, led by Liang Jiang, a professor of molecular engineering at the University of Chicago's Pritzker School of Molecular Engineering, working alongside collaborators at Harvard, Caltech, the University of Arizona, and the quantum computing company Quera, proposed using what are called reconfigurable atom arrays. In this approach, individual neutral atoms, the physical stand-ins for qubits, are held in place using tightly focused beams of laser light, sometimes called optical tweezers. Critically, those laser beams can physically pick up and move the atoms around between rounds of computation, letting far apart qubits temporarily come together, exchange information, and then separate again. Instead of needing permanent long-range wiring baked into the chip, you just physically shuffle the qubits into whatever configuration the error correction code needs, moment by moment. The elegance of this solution is that it sidesteps the hardware problem entirely rather than trying to brute force through it. Nobody figured out how to build a chip with a wire between every possible pair of distant qubits, because that kind of wiring density is essentially impossible to manufacture at scale using anything like today's fabrication techniques. Instead, the atoms themselves become the wires. A neutral atom sitting in one position can be lifted by a laser beam, physically transported across the array, set down next to a completely different atom it needs to interact with for that specific round of error correction, allowed to interact, and then transported right back to where it started, all in a matter of microseconds. It's a strange thing to picture, laser light physically rearranging individual atoms like pieces on a chessboard thousands of times per second, but that rearrangement is precisely what makes the mathematically superior QLDPC codes finally practical to build in real hardware rather than just something that looks good in a physics paper. Zhang summed up the significance of this plainly in the university's own announcement of the work. In his words, the proposed blueprint reduces the overhead required for quantum error correction, opening up new paths towards scaling up quantum computers. That is a carefully understated way of describing what their simulations actually showed. According to the published research, which appeared in the peer-reviewed journal Nature Physics, this QLDPC-based architecture using reconfigurable atom arrays begins to outperform the traditional surface code with as few as several hundred physical qubits, a dramatically smaller starting point than anyone had achieved before. And when the researchers modeled this approach at the kind of scale a genuinely useful quantum computer would eventually need, their simulations pointed to something close to an order of magnitude reduction in the physical qubit overhead required, potentially bringing the total qubit count needed for meaningful fault-tolerant computation down from the millions into the tens of thousands. Let that sink in for a second, because the scale of that shift is almost hard to process. This isn't a 10% improvement or a clever tweak that shaves a little off the top. If the projections hold as engineers move from simulation toward physical hardware, you are talking about needing somewhere close to 1/10 to 1/20th the number of physical qubits to reach the exact same computing capability. That is the difference between a quantum computer that requires an entire building full of cryogenic hardware and one that might realistically fit inside a research lab, years earlier than anyone expected. Now, it's worth being precise about what this research actually is and isn't, because the honest version of this story is still exciting without needing to oversell it. When this was first published, it was a theoretical and simulation-based blueprint, not yet a fully built machine running the algorithm end to end. The researchers proved the mathematics of fault tolerance for their proposed protocols, and they ran detailed simulations showing the approach should work under realistic noise conditions using hardware capabilities that reconfigurable atom arrays had already demonstrated experimentally in other contexts. That distinction matters. This wasn't a hypothetical dream sitting purely on a whiteboard. Every individual piece of hardware this blueprint depends on, moving atoms with laser tweezers, controlling neutral atom qubits, had already been separately demonstrated in real labs. What Zhang's team did was show, mathematically and through simulation, exactly how to combine those already proven pieces into an error correction architecture that could finally make QLDPC codes practical. And this is exactly why the story has kept building momentum rather than fading after its initial publication, because in the time since, other research groups working independently have been racing to turn this kind of blueprint into physical reality, and the results keep landing in ways that support the original thesis. Just this spring, a team working with Quera published follow-up research building on a related mathematical technique, using something called affine permutation matrices to construct even more efficient QLDPC codes, achieving encoding rates above 50% on neutral atom hardware while keeping logical error rates extremely low. That specific demonstration was limited to preserving quantum information correctly over time, known as quantum memory rather than running full computations. But it's a direct, hardware-level validation of the exact philosophy Zhang's team proposed, that reconfigurable neutral atoms are the missing piece that finally makes QLDPC codes buildable rather than theoretical. Around the same time, IonQ, working with trapped ion hardware rather than neutral atoms, published a demonstration showing they could run 9 different families of quantum error correcting codes, including QLDPC codes, alongside more traditional topological and concatenated codes, all on a single device without needing to physically reconfigure the hardware between experiments. That result matters for a slightly different reason. It shows the broader industry converging on the same conclusion from multiple directions at once, that flexible, reconfigurable qubit connectivity, whether through moving neutral atoms or through the natural all-to-all connectivity of trapped ions, is the key that unlocks these more efficient error correction codes across more than one type of quantum hardware. And separately, a team at Atom Computing announced they had achieved the first sustained multi-round quantum error correction ever demonstrated on a neutral atom system specifically, using what's called a toric code, another sign that the underlying hardware platform this entire approach depends on is rapidly maturing in real labs, not just on paper. None of this means a fault-tolerant, million times more powerful quantum computer is shipping next year. It doesn't work that way, and any honest account of this story has to say so clearly. Building a full working quantum computer around this architecture still requires scaling from simulations and small demonstrations up to systems with thousands of qubits operating together with extremely low error rates, sustained continuously over long enough periods to run genuinely useful algorithms. That is an enormous engineering challenge that involves manufacturing, laser control precision, real-time error decoding speed, and dozens of other hard problems that don't disappear just because the underlying math got dramatically more efficient. Industry roadmaps from companies like Quera currently point toward around 100 logical qubits by the end of this year, with the jump to systems large enough for truly transformative applications still expected to take several more years beyond that. But here's why this specific breakthrough deserves to be treated differently than just another incremental quantum computing headline. Nearly every previous improvement in this field has come from making individual qubits slightly better, slightly less noisy, slightly longer lived. Those are important, hard-won gains, but they are incremental by nature. What the University of Chicago team did instead was attack the structure of the problem itself. They didn't just make the qubits better. They changed the rules of how error correction gets built in the first place, showing that the theoretically superior class of codes the whole field already wanted to use was buildable all along. If you were willing to stop thinking of qubits as fixed points on a static grid and start thinking of them as physical objects, you can pick up and move exactly where you need them. That reframing has ripple effects far beyond one paper or one lab. Every application people talk about when they talk about the promise of quantum computing, simulating new drug molecules atom by atom, designing next-generation batteries and materials, modeling climate systems with a level of precision classical supercomputers cannot reach, even breaking the encryption schemes that protect the modern internet, all of it depends on first solving this exact overhead problem. You cannot run a genuinely transformative quantum algorithm on a machine that needs millions of physical qubits just to hold a few hundred logical ones steady. Every single one of those far-off future applications gets meaningfully closer the moment the qubit overhead requirement drops by an order of magnitude, because it changes what counts as buildable within the next 5 to 10 years rather than the next 25. Consider what this could eventually mean for drug discovery alone. Simulating the exact quantum mechanical behavior of a single, moderately complex molecule, the kind of simulation that could reveal why a candidate drug binds to a particular protein or fails to, is already beyond what classical supercomputers can do with full accuracy, because the number of possible quantum states involved grows exponentially with the size of the molecule. Pharmaceutical companies have been circling quantum computing for years, specifically because of this potential, but every serious roadmap for actually getting there ran into the same wall, needing far more reliable logical qubits than anyone could realistically wire together. If the overhead required to build those logical qubits genuinely drops by a factor of 10 or 20, the timeline for a quantum computer capable of simulating clinically relevant molecules doesn't just move up by a year or two. It could move up by the better part of a decade, because so much of the delay in this field has always come from raw hardware requirements, rather than a lack of good algorithms waiting to run on them. The same logic applies to materials science and clean energy research, where scientists have long wanted to simulate things like next-generation battery chemistries or novel superconductors at the quantum level, work that would let researchers screen thousands of candidate materials computationally before ever synthesizing them in a lab. And it applies, more soberly, to cryptography and cybersecurity as well. The reason governments and security agencies around the world have been pushing so hard toward what's called post-quantum encryption, cryptographic methods designed to resist a quantum computer's unique mathematical advantages, is precisely because the day a sufficiently large fault-tolerant quantum computer exists, today's most common encryption standards become breakable in hours rather than the billions of years they'd take a classical computer. Every serious reduction in the qubit overhead required to reach that threshold is also, quietly, a reduction in how much time the world has left to finish rolling out quantum-resistant security standards before it matters. It's also worth pointing out just how quickly the surrounding field has moved to validate, extend, and stress test this idea rather than quietly ignore it, which is often the clearest sign in science that an idea is genuinely onto something real. Within roughly 2 years of the original proposal, independent teams at Quira, IonQ, and Atom Computing had each published results that either directly built on the reconfigurable atom array approach or confirmed pieces of the same underlying thesis using different hardware entirely. In a field where plenty of theoretical proposals sit untouched for a decade before anyone tries to build them, having multiple serious labs racing to implement variations of your idea within 2 years is a genuinely strong signal that you found something real. It's worth remembering, too, just how competitive and well-funded this corner of the industry has become, which helps explain why the follow-up work arrived as quickly as it did. Quira alone raised roughly $230 million in a funding round in 2025, specifically to keep pushing neutral atom quantum computing forward, on top of an earlier $30 million round just 2 years before that. Money like that doesn't chase ideas that look shaky under scrutiny. It chases ideas that look like they might actually work, and it tends to accelerate exactly the kind of independent replication and extension that turns a single promising paper into a broader, field-wide shift in direction. When you see 3 or 4 separate, well-funded labs all pivoting toward validating pieces of the same core idea within a couple of years, that's usually a much stronger signal than any single headline result, no matter how impressive that one result looks in isolation. So where does this leave the actual timeline for useful quantum computers? Nobody serious in this field is claiming we're there yet, and the honest researchers behind this work have been careful not to claim otherwise either. What has changed is the shape of the remaining challenge. Before this blueprint, the industry's problem was twofold and arguably impossible in combination. Build individual qubits good enough to survive long computations, and simultaneously find a way to wire together millions of them without the entire system collapsing under its own physical complexity. This research doesn't solve the first problem. Qubits are still delicate, and they still need to keep improving. But it takes a serious swing at the second problem, showing a credible, partially validated path to needing dramatically fewer of those delicate qubits in the first place. That's not the whole mountain climbed. It's the discovery of a route up the mountain that is measurably, provably shorter than the one everyone had been climbing before. And there's something worth sitting with in how this breakthrough actually happened, because it says something about how progress in this field tends to work. Nobody at the University of Chicago invented a new kind of atom or discovered some previously unknown law of physics. They took a mathematical idea that had existed for years, a hardware capability that had already been separately demonstrated in other labs, and asked a genuinely creative question nobody had quite framed the same way before. What if the fixed architecture of a quantum chip didn't have to be fixed at all? Sometimes the biggest leaps forward in a field this technically demanding don't come from a brand new discovery bursting out of nowhere. They come from someone looking at 2 pieces the whole field already had sitting on the table and realizing, for the first time, that they fit together. If this story matters to you, follow along for what happens as these atom array quantum computers actually get built at scale over the next few years.